This is Primary Aerodynamics podcast number 15, and today we're looking at multi-rotor aerodynamic interaction of drones. So pretty much every drone on the consumer and prosumer market has more than one rotor. Usually they have like 4 or 6 rotors, and they're those things you can buy in electronic stores, that people use to spy on their neighbors conspicuously. And so having those rotors next to each other, they can interact and affect how well each one performs. And to do this, we're going to be looking at this paper called Multi-Rotor Drone Aerodynamic Interaction Investigation. And you can find this is open access, so you can look at it yourself if you like. So in the abstract, they say aerodynamic interactions between rotors are important factors affecting the performance of in-plane multi-rotor unmanned aero vehicles or drones, which are the majority of small-size UAVs. Optimal design requires knowledge of the flow features. The low Reynolds number of many UAV rotors raises the question of how these features differ from those expected by traditional analytical methods for rotorcraft. Aerodynamics of a set of side-by-side rotors in hover over a range of rotor separation and Reynolds number is studied using high-speed stereo particle image velocimetry and performance measurements. So that's pretty cool using PIB. And then they go on and just give briefly saying a dip in rotor efficiency at small rotor spacing at low Reynolds number is observed through thrust and torque measurements. So this was just that one particular parameter specifications that they had. They had other parameters that they looked into as well. So in the introduction, they said quadricopters, hexacopters, and in-plane octocopters appear to dominate the current commercial and recreational markets for vertical takeoff and landing UAVs, so VTOL UAVs. Interestingly, aerial vehicles do not scale down well in terms of aerodynamic efficiency and effective performance. Some of the most common present-day applications of small-sized VTOL UAVs are aerial photography, remote sensing, surveying, accidents, scene investigation, etc. The current aerodynamic knowledge in the small-scale regime is limited to design optimization of isolated rotors, with multi-rotor configurations being designed largely on an ad hoc basis. So what that means is they investigate just one rotor and they look at what the aerodynamics of that is. And then they assume that if you just put all these rotors together, they're still going to perform in the same way, even though they may interact with each other in real life. But that's why there needs to be more research to see how putting 2 rotors together or more affect each other's performances, because they could be like stealing each other's air a little bit or washing some of the wake into each other's wakes, which then affects their thrust performance, and they also have potentially an upstream effect from there. So going on with this paper, the current aerodynamics knowledge a good understanding of rotor-rotor and rotor-body aerodynamic interactions for multi-rotor UAVs is important for well-informed design optimization to push beyond the current performance limitations. So, for example, one current limitation for drones is that they can't really travel that far. There are some that can go pretty far and quite fast and have good flight time, but others don't, and most of them don't. So in order to make them more efficient, you need to understand how these rotor-rotor interactions are occurring and the rotor-body interactions are occurring to make them more efficient so that they can fly longer and further. So going on, knowledge and tools created over a span of about a century for helicopter rotors are not directly valid for most UAVs due to the high difference in Reynolds number range. The approximation used in helicopter rotor theories are primarily based on the assumption that very high Reynolds number flows act most like inviscid irrotational flows everywhere except in small regions containing high vorticity. Thin boundary layers and strong, tightly concentrated tip vortices and thin vortex sheet wakes are assumed in calculations that use the blade element, prescribed wake, and free wake methods. Outside these thin regions of vorticity, the flows were assumed to be inviscid, irrotational, and hence amenable to potential flow methods. So let's talk about this a little bit, because first of all, potential flow methods. Potential flow methods are fairly common. They used to be very common before CFD became viable. And one of the main reasons why is because they assume inviscid flow, which means you don't need to worry about viscosity in the calculations, and it makes the equations you solve way simpler and quicker to do. And so that means you can actually do them even a little bit by hand. Like back in the 1940s, 1950s, there were some researchers doing these panel methods by hand, very simplistic ones. if you want to look at panel methods, and you can use them on a computer, you can look up potential methods of panel methods and lifting line theories. So there are a bunch on the internet for free that you can just download and then plug in like your geometry that you want, and it will solve it for you. And for high Reynolds number flows, as I said here, for like, for example, helicopters, for most of the flow potential methods, such as panel methods, are quite accurate. But then when you go to low Reynolds number flows, such as UAVs, they become less accurate. So moving on. At low Reynolds number, the effects of viscosity become more comparable to inertial effects. Hence, helicopter rotor theories based on the above assumption of high Reynolds number cannot be expected a priori to give reliable predictions. So in other words, like now we sort of assume that these potential flows methods are going to be good for a situation that they're not really haven't been investigated for that much. So we're creating this assumption that turns out to be false, and then it just keeps on repeating itself. So we need to research if that's actually true, and if not, how to break out of that. So to what extent can these methods be trusted, and how much do they affect predictions when there are multiple rotors in close proximity? These are the motivating questions behind experimental research presented in this paper. The prior studies relevant to the problem can be separated into low Reynolds number airfoils, low Reynolds number rotors, and large-scale multi-rotor vehicles. In the area of low Reynolds number rotors, research so far has been in performance measurements, design optimization, and CFD of micro-air vehicles scale rotors, so MAVs. All in-plane multi-rotors can be interpreted as pairs of rotors placed side by side. Hence, studying one pair of side-by-side rotors at a range of conditions should provide a fair idea about all possible in-plane configurations. And then their present study looks into this. So they look at two rotors placed side by side at different distances away from each other, expressed as a function of the radius of the rotor. And they say that this present study uses PIV and performance measurements to investigate how these side-by-side rotors are affected by each other. And one thing that they do look into is something called the figure of merit. This is something that is somewhat known, like it's in the circles where you do look at the figure of merit. Everyone knows it, but I'm just going to go through it just now so you understand if you don't. So the figure of merit, generally speaking, is just a number that we calculate to determine how efficient typically a rotor system is, so helicopters or a drone, etc. And in this paper, they're calculating their figure of merit, the combined figure of merit of the entire UAV, as the coefficient of thrust of the left rotor to the power of 1.5 plus the coefficient of thrust of the right rotor to the power of 1.5. So it's summated that divided by the square root of 2, and then dividing all of that by the coefficient of torque of the left plus the coefficient of torque of the right. And then you just get a number, and that way you can compare how the entire vehicle is performing based on these different spacings. And they go on and plot these figures of merits. They say, starting with the figure of merit plot in figure 3, which is one of the figures in their paper, it is seen that at 80,000 Reynolds number Ks, there is no noticeable variation in the figure of merit over the range of axis shifts. So they move these rotors from very close to fairly far away, and the figure of merit didn't really get affected. And this is at a Reynolds number of 80,000. This was a quite high one for them. However, at 40,000 Reynolds number, the figure of merit cases tends to increase slightly with increasing distance between the rotors. This slight increase for 40,000 Reynolds number cases is significant only for a distance between the two rotors of less than 2.3 times the radius, after which it is approximately similar to 80,000 Reynolds number cases. So in a nutshell, what this is saying is at higher Reynolds numbers, putting these two rotors close together doesn't really seem to affect the overall figure of merit of the UAV. When you drop the Reynolds number, then when you starting to get quite close, it does drop the figure of merit. And the limiting case is 2.3 times the radius. So effectively, just as long as you place these two rotors the same diameter apart, then they're fine. And they go on and discuss why this occurs. So they use their PIV results to look into it. And they say the rotor tip vortices due to the two adjacent rotors interact with each other for small axis shift values. So that's something interesting to note. So there are tip vortices that occur from rotors because you're producing a lot of lift or thrust at the tip. And then you're producing these vortices because of the pressure differential. And then these two vortices are interacting with each other. Now, you could always reduce the amount of lift that you're producing at the tip. The problem with that is that rotors typically produce their greatest thrust at the tip as well, because that's where they're traveling fastest and all that. So you can reduce the lift, but then that's coming at a price of reduced thrust as well. And it's dramatic. So moving on, they say they lose their coherent structure in about a rotor rotation and get split into small spots of high vorticity in the region between the rotor wakes. Very often, consecutive tip vortices from the same rotor are seen to roll about each other after getting disturbed from their trajectory by velocity induced by vortices from the neighboring rotor. The direction of vortex roll-up is the same as the direction of vorticity in the vortices. These pairs of vortices eventually merge and then split into spots of high vorticity soon after. So in other words, what they're saying is a coherent wake of one rotor is now just getting chopped up and mixed all together and becoming incoherent when you put it next to another rotor. And they go on and say such wake interactions are relatively higher for 40,000 Reynolds number cases compared to 80,000 Reynolds number cases. With increase in axis shift, so when you put the two rotors further apart from each other, the trajectories of tip vortices tend to get more predictable and the region between rotor wakes become free of sporadic flow. So in other words, they become more independent and they can follow what they're supposed to usually do without too much interference from each other. Lesser wake interactions at higher axis shifts is in a way obvious and expected as velocity induced by vortices decay by a factor of the square of the distance outside the solid body rotation core area. So let's discuss this quickly. So when you have a vortex in anything, like it can be stationary area, it can have a velocity or whatever. If you have a vortex, it's going to be inducing the flow around it and swirling that. Now, the amount that it induces this flow is directly proportional to the inverse of the square of the distance away. So if you're at 1 meter away from a vortex, let's say you have induced velocity of 1 meter per second. When you go to 4, then you have 1/16 of that squared. It's proportional to the inverse of the square. So moving on, they say the wake should in principle be like that of a single isolated rotor as axis shift tends to infinity. Does that make sense? The further away you get from each other, the less influence you have. The low Reynolds number cases see more wake interactions, probably because the tip vortices are weaker in terms of circulation, and downwash convecting them downward is also lower. These slow-moving vortices with low circulation are more vulnerable to velocities induced by flow features in close proximity, such as vortices from the neighboring rotor. So that kind of makes sense because they're not nearly as concentrated. They can be messed with a lot more. They're not as strong. At higher Reynolds numbers, and hence higher thrust values, the vortices are stronger and they also get lesser time to get affected by other disturbances due to stronger downwash. So what this means is when you're traveling at higher velocity, higher Reynolds numbers, so the rotor is spinning faster, you're producing more thrust. And this is then jettisoning out the wake faster, and then that way it gets clear of the other rotor wake interaction much quicker. So that's one of the reasons why there is less interaction when you have a high Reynolds number. So moving on. Similar observations were made regarding relatively higher wake interactions for low Reynolds number cases in the previous work on quadricopters. So a quadrotor, sorry. This is reference 23 in this paper, where the Reynolds number of 8,630 test case shows significantly higher wake interactions compared to the Reynolds number of 16,856. The figure of merit for the lower Reynolds number case was also much lower than the other two higher Reynolds number cases. just like it is in the current study, where the figure of merit is lower for the Reynolds number of 40,000 at low axis spacings of the rotors, so when the rotors are very close together. It is possible that the low rotor performance at small axis shifts at low Reynolds number is because of flow that is induced over the blades by interaction with tip vortex cores of the adjacent rotor. Tip vortex cores are known to be larger in size for low Reynolds number rotors. So that's pretty interesting. Like, even though the vortices are going to be stronger for higher Reynolds numbers, the cores are smaller, so they're more concentrated. And as you reduce the Reynolds number, they become more dispersed, I guess, when they come out, you could say. If interactions of rotor blades with adjacent rotor tip vortices is a factor, then phase difference between the rotors should also play an important role in performance. Verifying that will need a setup where the rotors are mechanically linked to allow locking their phase with respect to each other. This is really interesting. So they're saying that these tip vortices are really things that are probably the primary reasons why the rotors are interacting with each other and they're not making the other rotor perform as well. So then they're saying that, well, if that's the case, then if you make it such that these rotors are spinning out of sync, so when one blade comes around, there isn't a blade of the other rotor coming around, then that should be able to create this way that the vortex coming off of that tip at that point can steer clear of the other vortex coming off the other blade tip, which is out of sync. It's further behind in the rotation. So by putting them out of sync, you can perhaps increase the figure of merit at these lower Reynolds numbers at very close spacings. So just here, I want to just briefly say, make sure to check out the International Aerodynamics Conference we put on every year in October. Check out the experimental instrumentation we make to make your experiments better, and check out the courses we make to make you better aerodynamicists. All the links can be found in the description. Make sure to like and subscribe to this. So moving on now. They then compare the figure of merit data for the current bi-rotor tests with those from the previous tests on the quad rotor, which they did in a previous research campaign. It can be noticed that the rotors in the current tests perform worse than the quad rotor rotors, despite being operated at a much higher Reynolds number. The biggest difference between the two setups, other than the size, is blade geometry. The blades used in the current setup are symmetric and more like those for large-scale helicopters, whereas the quad rotor blades are highly cambered. Such highly cambered blades are ideal for low Reynolds number rotors only where the viscous skin friction drag is high enough to afford highly cambered airfoil designs, which otherwise would have caused a much larger share of pressure drag. So that's interesting. That's another parameter to look out for, the profile of the blades. They made a big difference. It is noticed that from the streamlined plots, the mean rotor weights of the two rotors tend to stay farther away from each other for 80,000 Reynolds number cases, hinting towards lower wake interactions at higher Reynolds number apparent from the instantaneous vorticity contour plots as well. As the axis shift increases, the flow around the rotors slowly tend to be similar to that expected of an isolated rotor. So that makes sense. The streamlined plot for a Reynolds number of 40,000 and an axis shift of 2.1 times the radius, so almost an entire diameter, is noticeably different from the rest. The first plot shows high velocity magnitudes in the region between the two rotor wakes due to rotor wake interactions. Outflow profiles under both rotors are wedge-shaped, with velocity magnitude increasing while going from the rotor hub to the rotor tip and dropping back to zero steeply right after the tip. So let's talk about this quickly. So the outflow profiles is effectively what the wake is. You have this rotor spinning around and it's shoving air through, and then what is coming out as the velocity, that's the outflow profile. And as I was mentioning before, this outflow profile increases in velocity as you go from the hub to the tip because the tip is moving faster. And interestingly, we'll get into in a second, the peak in outflow velocity profile is consistently found close to a radius of 0.9 radius span-wise location for both rotors for all cases except the Reynolds number of 40,000 and an axis shift of 2.1 times the radius, where it is seen slightly inboard close to the hub. Well, what that is saying is the maximum velocity that you're going to see in the wake is going to be at about 10% in from the blade tip, 0.9 times the radius. However, for this particular case, a Reynolds number of 40,000 and an axis shift of 2.1 times the radius, this is actually even more in board, closer to the hub. And it's such a wedge-shaped feature is common for most rotors, especially if the blades are simple rectangular blades like the ones in this study. So they're saying that the profiles aren't that surprising when you have these rotors very far away from each other. That's what they should be. It should be noted that the velocity profiles, which are non-dimensionalized using the rotor tip speed, are almost exactly the same for the two Reynolds numbers for the axis shift of 2.2 times the radius, 2.3 times the radius, and 2.4 times the radius. Now, this is interesting because if you remember from earlier, they said that at 2.3 times the radius, that's when the figure of merit is no longer affected by the axis shift if it gets larger for a Reynolds number of 40,000. However, for 80,000, the entire range, it wasn't affected. So it's now they're saying at the axis shift of 2.2 and upwards, the velocity profiles are looking very similar, which is what you'd expect is around that 2.2, 2.3 region, which is where the 40,000 Reynolds number case starts to become indifferent to the spacing between the rotors. So that's why there is this similarity. And they go on and say that this may mean that at least in this range number, the Reynolds number does not have any significant effect on the way the inflow and outflow velocities get induced when the rotors are farther than 2.2 times the radius. So in conclusion, they say a dip in performance was observed for cases with rotors very close to each other at low Reynolds number. It was hypothesized that their interaction of rotor blades with the tip vortex cores of the neighboring rotor blades at small axis shifts could be a reason for the effect of efficiency. However, more focused tests are needed to confirm this. The instantaneous flow field measurements indicated high inter-rotor wake interactions for small axis shifts, causing rotor wake features to distort, lose coherent form, and deviate from their typical trajectories. So that's to be expected when you have all these vortices interacting with each other in different jets effectively coming at each other. They're going to interact and they're going to screw each other up to some extent. And briefly summarizing the key findings: 1, very close proximity of adjacent rotors adversely affect rotor performance. 2, blade vortex interaction hypothesized to be a reason behind the noticed effect on performance. 3, high inter-rotor wake interaction observed for close proximity rotors at low Reynolds numbers. And 4, similarities observed in instantaneous and mean flow fields for the range of tested conditions, useful in extending the understanding to a wider range of vehicle configurations. Okay, so that's it. Make sure to like and subscribe. Check out our instruments that we make, check out our courses, and check out the conference that we put on. All links in the description. Peace out.